It's wonderful to see you all, and I know it's afternoon for you. It's very early in the morning here, and we hope it's going to be a nice day. We haven't had many nice days here. It's been very cloudy for the last few days, but now it's brightening up. So let's hope we have a nice day. Nice to see you all. And today's session is about dry pipe models. Not only that, there are associated items such as air release valves and so on. And before I actually go any further, could one of the other organizers confirm that you can see my screen? Victoria,
yes,
can you confirm that I can see my screen?
Yes, we can see your screen, Dr. Sebastian.
Very good, thank you. Now, this is a kind of system I'm talking about. See, if you look at this pipe, the initial state is wet, but what will happen to this pipe is it'll become dry and then it'll become wet again. So the dry pipe model typically it models pipes whose initial state is dry, but progressively the pipes get filled with water. We call it priming, and the pipes get primed gradually, one by one. But the PIPENET dry pipe model is not limited to that. A pipe could also start with a wet state, as it's here, and then it can become dry, and it can become wet again. So remember that this is an example where, see, what will happen is that this pipe, this valve, you see, we're using the linear profile. So it closes, it's open up to 5 seconds, and at 10 seconds is fully closed. In other words, it closes, you can see it here, from 5 to 10 seconds, and it stays closed until 50 seconds. And then at 50 seconds, it starts to open again. And by the time we reach 60 seconds, it's fully open. That's what happens to this valve. And of course, initially, the pipes are all wet, or you can call it flooded. But when the valve closes, because of the momentum of the liquid and also the static head, you can expect air to come in through this vacuum breaker. You'll see that this has a slightly different symbol from the traditional vacuum breaker model in PIPENET, because we call this the air valve. It's a different model from the vacuum breaker model. It's here. That's the vacuum breaker model. And if you look at the attributes of that, you see the air inlet valve is 15 millimeters diameter, and outlet valve is 0. In other words, this is purely a vacuum breaker valve. So it doesn't offer any path for air to go out through this valve. On the other hand, if you look at this valve, that again is an air valve, you can see here. And that has an air inlet of 0 and outlet of 50 millimeters. So this is an air release valve, which can only allow air to go out. It cannot allow air to come in. So that is a very, very quick introduction about the dry pipe model and the associated items such as the air valve and so on. And here what we'll see later is that you can actually see how the air pocket moves along this pipe when this valve closes, and then, when the valve opens again, how the air goes out through this valve. It's actually quite a beautiful simulation. So how do we actually define a dry pipe? Options, module options. See, and we have this option here. If you, for example, have a dry deluge system, you may want to check this radio button because you would want all the pipes in the deluge system to be dry. You can choose this option. Well, of course, you can treat all pipes as wet, which is the option where all the pipes are flooded and they remain flooded throughout the simulation. They have no option of going to the dry state. Now, you would have, of course, come across the term dry pipe 1 model and dry pipe 2 model. Dry pipe 2 model actually is one of the facets of the model of PIPENET, because if you actually consider dry pipe 2 model, it can work in conjunction with an air valve, and it can allow air to come in. So that's why it's called air cushioning effect. It's not called dry pipe 2, because there are other items which actually work in conjunction with the dry pipe 2 model. That's a basic introduction to how you choose the dry pipe model. So if you want to use dry pipe 2, you must click on this, and that will bring in other options, such as the air valve being active. Okay, now, before we go on to the actual simulations, let's look to see what's the need for the dry pipe model. Because we have the need to model expulsion and inlet of air into a piping system. A deluge system is a classic example of that. But it's not only a deluge system. So you can calculate accurately the filling time of deluge systems. We need the dry pipe model for that. It's not only deluge systems. It could be priming of general systems. It could be, for example, a pipeline or a cooling water system where initially you need to flood the system. Or it could even be a dry firewater ring main, because there are systems where the complete firewater system is dry to begin with. Typically, you'll find that in unmanned platforms, but there are other reasons why the ring main itself could be dry. So it's not only deluge systems, it can be used for many other systems. So but the use today is mostly for priming deluge systems, but people are beginning to use the dry pipe capability for general systems. Calculation of pressure surge at the end of priming. Because when you think about it, let's consider a deluge system. A deluge system is dry. The nozzles are not delivering water. And what happens when you open the deluge valve? The pipes get primed one by one, and the nozzles deliver water one by one. And PIPENET can model all that. But the last nozzle that actually started discharging water is a special one. Why? Because it's much easier for air to escape through a nozzle than for water. And so when the water reaches the last nozzle, there's a sudden deceleration of the whole system. And as you know from the earlier webinars, if there is a sudden change in the momentum, that will lead to a pressure surge. So the last nozzle could potentially lead to pressure surge. And we'll have a look to see how we can mitigate against that. And that is what this is about. It's very, very simple mitigation techniques. All models have limitations. Why? Because a model is nothing more than a mathematical representation of the real system. And we can never model the real system exactly. So models always have limitations. It doesn't matter what it is. It could be HYSYS, or it could be PIPENET. They will all have restrictions on the modeling capability. It's the same with the dry pipe models in the transient module. But this is obvious. A dry pipe can only model pipes. It cannot model a pump. So that's an obvious statement. Secondly, the friction loss caused by the air column can be neglected. Why is this? Because air, typically in a piping system, has a much higher velocity than a liquid. So, you know, with a liquid, perhaps the velocity would be 3 meters per second maximum, whereas for a gas, it could be 20 meters per second or even more. So it's much higher. So if you consider a deluge system, the air will move at the same speed as the water. So it'll have a much lower velocity. And as you know, velocity is the main component in the friction loss. So we can assume quite rightly that the friction loss in the air column can be neglected. That's an assumption made in the model. The pipe may only have one bubble or one slug. That's a limitation in the dry pipe model at this point in time. Dry state of a pipe and channel cavitation may not coexist. This again is obvious because a channel cavitation is a proprietary model. It's a model that we've developed ourselves, and that has a vapor cavity in the pipe. Now you can also cannot have an air cavity in the same pipe, because then the model will not work. You cannot have air and vapor mixed together in the cavity. So that's a problem. So that's why this limitation exists. And I would suggest that this limitation is really not a real limitation, because I can't think of a system where you could have channel cavitation and dry state of the pipe together, because if a pipe is dry, the cavity will collapse typically. The last assumption, this also is not really a limitation, it's obvious, because we assume that the air and the liquid move at the same velocity. Now, let me just add one more point that's implied by this. A pipe is treated as a one-dimensional model. And because it's a one-dimensional model, there's an underlying assumption that the flow of liquid is a plug flow. In other words, it has a very clear front. There is no, because we're not modeling 3D, we don't have air and liquid moving together. In other words, there's no stratified flow. So the air column and the liquid column, there's one interface, and they will move at the same velocity. This is kind of implicit in the fact that we're assuming a one-dimensional model, and so it's not really an artificial limitation. Dry pipe 1 and dry pipe 2, you heard me mention those, and what are the differences? The first thing is dry pipe 2 is one part of what we call cushioning. If we consider cushioning option, then the dry pipe model 2, dry pipe 2 model is automatically used. But we can also use other models such as the air valve and so on. However, what is the difference between dry pipe 1 and dry pipe 2? First of all, the dry pipe 1 assumes that the air pressure is 0. This is substantially true because the air in a deluge system, for example, remains approximately at 0 bar gauge until the last nozzle begins to deliver water. And we can compare the two options. Whereas dry pipe 2 assumes that the air pressure is not necessarily 0, and it models the air column by the ideal gas law, which is PV equals MRT or NRT or whatever, it doesn't matter. It depends on your definition of the gas constant. So this is the most important difference between the two. Dry pipe 1 assumes that there is no obstacle to airflow to the exit. That's also more or less implied in this, because if there was an obstacle, we cannot assume the pressure is 0 bar gauge. Whereas dry pipe 2 considers obstacles which are sonic or subsonic. And this can be relevant in systems where there is a pressure loss downstream of the dry pipe. And of course, it also, although I've not mentioned this specifically here, the dry pipe 2 model allows the modeling of air pockets, how air pockets move through the pipes. The example I showed, the network I showed earlier, the air comes in through the air release valve, then it's got to flow down the pipes until it reaches the air release valve, and then it gets expelled. So it actually can model the movement of air pockets in the system. That's dry pipe 2. As I said, it's not dry pipe 2 on its own. Usually is associated with something like an air valve. Dry pipe 1 model is usually faster because the model, you can see, is much simpler. And both models, of course, can give accurate results if the pressure is approximately 0 bar gauge. However, dry pipe 2 model can be more accurate if pressure is not equal to 0 bar gauge. These are the basic differences between dry pipe 1 and dry pipe 2. In general, it may be better to use dry pipe 1 unless you think it's necessary to use dry pipe 2. Okay, so let's start looking at some networks. I'm comparing dry pipe 1 and dry pipe 2 here. So you can look at the options. You see, the air cushioning effect is unchecked. So that's why, that means it's a dry pipe 1 model. And we've got new pipes dry. Now, if I look at this network, how do I know what the initial state of the pipes are? So display option, there is this option here, and that will indicate if a pipe is dry. It's a flag. See now, you can see that there is this hash sign. So this is a typical deluge system. The pipe upstream of the deluge valve is flooded, where all the pipes downstream is the initial state. You cannot say it is a state because its state is dry only initially. Gradually, it'll become wet. And all the pipes you can see downstream are dry. And the deluge valve opens from 5 to 10 seconds. And the inlet pressure has a constant value of 8 bar gauge. Strictly speaking, the pressure at the inlet will change with time because the 5-watt ring main, once we start drawing water from the 5-watt ring main, the pressure may go down. But in this example, we are assuming that the pressure can be fixed at 8 bar gauge. It approximately stays at that value. This may be the case because you, as an engineer, you're only responsible for this part of the system. There may be some other company that's designing the 5-watt ring main. And so hence, this may be the best assumption you can make. Nevertheless, we're assuming there is 8 bar gauge fixed, valve opens, that remains at 8 bar, and the system gets flooded. And we can see how the pipes get primed one by one, and then the nozzles discharge one by one. So let me run it. The first thing I'd like to show you look at the nozzle in the data window, look at the results, see there is this column, priming time, and if I click, reorders them in the increasing order, click again, reorders them in the decreasing order. So if I see there's a panel here and I'm going to move it and I click on that, it'll take me to the nozzle that primes last. And you know that the deluge valve opened from 5 seconds. So that means that the fire is detected at 5 seconds. So this takes 10.56 seconds for the system to start discharging. So that's the discharge time. So it's an ideal way to calculate. the discharge time. Let's look at it graphically now. You can also show the nozzle priming time in the schematic. And of course, you have the panel that shows the color coding. Of course, the red are the earliest and so on. Okay. You can also look at the maximum pressure in the pipes. It's quite high pressure, but we're not looking at the suppression of pressure surge here. We are simply using PIPENET Transient module to calculate the discharge time. But having seen these large pressures, we can then see how we can reduce the pressure surge. That's a different problem. PIPENET Transient module is used for two different purposes in fire protection. One is surge analysis, and the other one is discharge time calculation. And here, we're mainly interested in discharge time calculation. You can show that here. But let's look to see. See, look, this pipe, write it down, 1, 7, 11, 12, and nozzle 7, let's say 2, and 1. They're of interest to us. So let's have a look. Pipe 1. Personally, I tend to look at the air volume first because that shows, you can see that the pipe is full of air, and we know that it starts, the deluge valve starts opening at 5 seconds. So you can see that the air volume in that pipe 1, starts to go down, and the air is fully expelled at about 8.58 seconds. It's pretty quick. It's about 3.55 seconds. So let's look at the next pipe, which is pipe 7. There's a little bit of an optical illusion, but it looks as though this starts later than this. But in fact, you see, as soon as the air is expelled from the first pipe, the second pipe, the air starts getting expelled too. You can see that the axes have different scales, and you can actually combine them. So they have the same scale. And the next one is pipe 11. Volume of air. You can see that pipe 7, I think it's probably slightly longer than the other pipes, so it has a bigger volume. See if you look at that. That's 10 meters long. That's 10. See, that's 12. So that's why initially the volume is higher, but it starts losing air when the second pipe is full of water. And then we go to pipe 12. So you can see that the pipes are getting flooded one by one. These are the 4 pipes in the path leading up to that nozzle, which is nozzle 7. So if you look at nozzle 7, which is here, see, in the last pipe gets primed, the nozzle discharges water. So you can see how PIPENET models the progression of water along the dry pipes until we get to the last nozzle. Let me remove all the graphs because we want to now look to see what the nozzles are doing. Nozzle 1 is the first nozzle. You can see that there are some peaks in between. Why are there peaks? Because every time a nozzle in the system begins to deliver water, there's a little bit of a shock wave because it was delivering air initially, and that changes to water, which means that it slows down. So there is a little bit of a pressure surge, and that actually works. It's beautiful, really, because it works all the way back to the first nozzle and creates a small peak because there is a peak in the pressure. And if you look at nozzle 2, see, that's nozzle 2, and that's nozzle 1. So the interesting thing is that, you know, they all experience these little bit spikes because of the shock wave that travels back to them. Okay, and let's look at the last nozzle. See, that doesn't have these little peaks because that is the last nozzle which creates a shock wave. Now, if I remove the others, you can see that this has actually got these peaks, but that one, the last one, which is a green one, hasn't got the peak. I'll remove that as well. So we look at it. So it goes straight up, but it has an overshoot. Why does it have an overshoot? Is because the liquid in the pipe has a momentum which is higher than the momentum in its steady state. Why is that? Because as long as there is air in the system, it escapes more easily than the water. But when the water reaches the last nozzle, it decelerates. But it takes time to decelerate, so the initial momentum is higher than the steady state momentum. So there is a peak, which then comes down to the steady state. So that's what we're actually seeing. Now let's also compare that to this. Now you can zoom in. See, there are nice features in PIPENET, like this magnifying glass. You can see what's going on, you know, in a greater detail. You can also zoom in. I mean, you can zoom in by using this, or you can actually say, I want to look at 13 to 17 in more detail. So 13, you put 17, see, we're zooming in. You can see that the peak, you know, the peak actually starts in nozzle 7, and that works its way back to nozzle 1. And nozzle 1 also has a peak, but they seem to be almost, you know, simultaneous. They're not quite simultaneous. So let me try and exaggerate this a little bit. Let me make this pipe 50 meters long, so it will take longer to travel back. My conjecture is that the pressure surge starts here and it works back, and that creates a spike in the flow rate here. If I make this pipe longer, that will take a little bit longer, and there'll be a bigger separation between the spikes. That's the idea. So let's look at the flow rates in nozzle 7. Sorry, nozzle 7. It's slightly later because that's because previously it was around here, because that pipe was longer. Just to remind you, nozzle 1 is this nozzle here, nozzle 7 is there, and I'm saying that when the water reaches this nozzle, there will be a shock, and that shock wave will travel back, and that will create a spike in the flow rate here. And let's see how that happens. See now, so you can see let me make the y-axis the same. And I can increase the diameter. See, I can see that, well, I can make it even bigger. You can see that the spike in nozzle 1 happens a little bit after the spike in nozzle 7. I can do the same by zooming in. Zoom in between 22 and 25. So you can see that this is because I increased the length of that pipe, so there is the time difference is a little bit more pronounced. So that's at about 23.2, and that is about 23.1. So it's 0.1 second approximately. So you can see that my conjecture is correct. I'll put this back to 12. Do the simulation. Priming time is 15.6. I'll make a note of that. What I'm going to say, now, in a system like this, if I change to dry pipe 2, which is what I'm considering here, that's what I'm doing, because there are no air valves in the other models here. So when I switch this on, it simply changes the dry pipe model to dry pipe 2. So remove that to makes this a little bit clearer. So I'm going to run this. So if it's 15.7, so it's 0.1 second longer, but probably even less than that. It could be because of rounding that it's 0.1. And so it's, the two models produce virtually the same results. Now, let's see what happens if we change the nozzle K factor. In other words, I'm going to put a smaller value for the K factor and see if that makes a difference. So let me switch back to dry pipe 1. See, typically you would change the nozzle characteristic in the library, and you don't have to do all that. See, this is another trick that I want to teach you. I can make them all user-defined, and then change that to 22. So see how quickly I change the K factor for all the nozzles. The idea is to see what happens if I create more resistance in the nozzle. It's 15.4 seconds, slightly quicker, so I'll make a note of that. 15.4, dry pipe 1. By the way, why is it quicker? It's because the flow rate through the nozzles is less. See, so the flow rate through the pipes actually is quicker because these are taking less water. That's the reason why the discharge time is slightly shorter. So, when you have bigger pipes, in steady state, typically it's better because it's less friction loss. But when you're calculating the discharge time, it is not always an advantage to have big diameter pipes because they take longer to fill up. Keep this in mind. The second point you have to keep in mind is that the most remote nozzle is not necessarily the last nozzle to discharge. Okay, why? Because you see, this is a very, very simple example. It's difficult to illustrate. For example, I make these pipes very large and I do the calculation. This part of the system will get filled up more quickly than that part. So, you look at it and sometimes they say, hey, this is not right. The last nozzle to discharge is not the most remote nozzle. So something is wrong. No, it's not necessarily the case. The last nozzle to discharge is not necessarily the same as the most remote nozzle. Keep that in mind. So you can see that now it's a little bit more difference. It's 0.4 seconds because there is a bigger resistance to flow through the nozzle. So, so in this case, maybe even here, what's the difference between 15.4 and 15.8? It is within the kind of variation that you would accept in engineering. But you can see that there is a small difference if you use smaller nozzles. Let's go on to the second example. It's very similar to the first example, except it shows the elevation, and you can see that this part of the system is lower than that part of the system. There's one particular point I want to show in this, and it's a very important point from an engineering point of view. These are, previously I think it was 15.6, it's now 15.5. Why? Because the static head assists the flow through these nozzles or through the pipes, and hence that's slightly early. Now if we switch to right pipe 2, It's around approximately the same. So, we can see the dry pipe 1 and dry pipe 2 work in virtually the same manner. Let's look at the elevation here. See, these are +2. That's -2. Let's look at what's happening in pipe 2 and pipe 7. Let's compare them. Keeping in mind that pipe 2 is going up, whereas pipe 7 is horizontal. See, they start at the same time because air gets expelled from both pipes when pipe 1 gets full of air. But you can see that although this pipe is only 2 meters long in comparison to that pipe, which is 10 meters long, you would expect this pipe to take 5 times as long as that pipe, but it doesn't. It only takes around twice as long. Okay, so vertical pipes are bad news when it comes to discharge calculation. I'll make it slightly exaggerated. Take this pipe and say it's 5 meters long and it goes up 5 meters. So that's pipe 2 and that's pipe 7. Okay, let's look at pipe 2 and pipe 7. See, now they're actually getting primed more or less at the same time. See, so although this pipe is only half the length of that pipe, the priming time is the same. I'm not sure about that. Let's have a look at the nozzle priming times. In fact, you see this nozzle here, I didn't know this was going to happen. This nozzle here actually takes longer to prime than that nozzle, even though this nozzle is further away. Why am I emphasizing this? It's a very good reason for emphasizing this, because we've come across systems, we provide extremely good support, and it's an engineering company which had great difficulty in reducing the discharge time of a deluge system. And what the problem was, it was a problem that was extremely difficult to solve, because this pipe here had an elevation of around 35 meters or 40 meters. Because, from a maintenance point of view, it may be better to have this valve lower down on the platform. But the deluge system itself is at a high level. So this pipe had an elevation change of 35 to 40 meters. I cannot remember exactly what it was. I think it was probably 30 meters. And that meant, you see, it took a very long time for that pipe alone to get primed. Once this pipe gets primed, of course, the deluge system discharged very quickly. You cannot change the position of the deluge system. So the only way you can truly solve, only two ways, I suppose, is to, in either case, you would have to move the deluge valve to a higher level. You can tap from the fire watering main at the same position, but place the deluge valve at a high point in the system, or alternatively, you can connect to the ring main at a higher point. In either case, it is quite a substantial modification, which was unfortunate. So it is good engineering practice to avoid a big elevation change, especially the pipe that goes from the deluge valve in to the actual fire watering main, the fire water deluge system proper. In other words, the elevation difference between the location of the nozzles and the deluge valve, keep it as low as you can, because this pipe, an elevation change in that pipe can lead to very long discharge times. Okay, so that's the main point about this example here. And this here is a dry ring main. I will not run this because there are more important examples that you should look at. First thing you notice here is that there is no overboard dump system here, because purely from the point of view of the system startup, the air from the caisson can simply go into the dry fire watering main and the dry deluge system and simply go out. You don't need an air release valve here, and that's why the model is like that. And if you look at the module options, display, see everything. I don't know if you can see that, and make the lines slightly thicker. See, all the pipes, including the ring main, they are dry. Okay, as I say, I will not run this because it's not going to tell you much more than what we saw earlier. But we've got to be you'll find that in a system like this, sometimes that because the fire water ring main tends to have larger diameter pipes, you could get a shock wave, a high pressure surge, when the water gets into this pipe. Because the water flows at a high level, a high rate, because the diameters are big, and the air gets expelled, the water reaches here, and then suddenly you find that it decelerates. So it could lead to high pressure surge at that point in time. So you got to watch out for things like that. Okay. Let's look at, there is this concept. This was actually developed by Dr. Chen. By the way, Dr. Chen, he's made a special point to be here today because he's the developer of the dry pipe models. And so if you have any question, it doesn't matter how intricate it is, he's here to answer them. Then we have a pressure surge. You can introduce a buffer pipe to reduce the pressure surge in the deluge system. If you have time, I'll come back to this and run this because I think that there are some other examples I'd like to show. I wouldn't want you to miss them. And so if there's time, we can come back. Basically, all this means is that you do not end the range at the last nozzle. You extend that a little bit. See, that means air is trapped in the extension pipe. It doesn't make any difference because all the pipes are dry anyway. So when the system gets primed, that has a cushioning effect. You can model that with a dry pipe too, or with an accumulator. I've just chosen to model with an accumulator, as I say. And this is a very effective way of mitigating pressure surges which arise when the deluge system gets primed, at the end of the priming of the deluge system, because you can get some high pressure surges. It's a very simple solution. All you do is to extend the pipe and put a blank flange. As simple as that. Okay. Let's go on to, as I say, if there's time, I'll come back to that. A system other than fire protection systems. See, this is a SubC pipeline, and we can see that all the pipes are dry, except downstream of the check valve are dry, and this is connected to the storage tank, and there's an offshore platform. There's a pump that discharges water to a tank farm. And let's say our purpose is to calculate how long it will take for the system to prime. The pump starts. It takes 10 seconds to run up, starting at 5 seconds. Okay. This valve remains open all the time. And the pressure here is not zero because we're assuming that there is a storage tank and the pump is connected to the bottom of the storage tank. And the pipe diameter you can see is 800 millimeters. That's in old language is 32 inches. And the pipe lengths, you can see that's 10 kilometers long, 5, and so on. I think this is approximately 35 kilometers long. So you can see, I'm going to run this. I can actually speed this up by increasing the time step, but I'm not bothered. I mean, I've set the time step to 0.15 because the simulation time is 6,000 seconds. This could have been made a little bit bigger, in which case it would run quicker. Anyway, we want to see when pipe 13 primes. So we can look at the flow rate through valve 1. We can see that the pump starts at 5 seconds. Valve 1 and the flow rate. See, that's happening at approximately 4,603 seconds. So I'm making a note of that. See, quite long. That's why the simulation time had to be 6,000, because it takes a relatively long period of time. That's, what is it, 460 divided by 6 is about, it's more than 1 hour. You know, it's probably 1.6 hours or something like that. Anyway, it doesn't matter. You just, you know, it shows that it takes a fairly long time. Let us see what happens if we use dry pipe 2. So you can see it's slightly longer. It's 4753. So that's about 150 seconds longer than dry pipe 1 model. So there is even here, it is not, I wouldn't say it's a very big difference. You know, 150 seconds out of 4,600 seconds, within engineering terms, you would accept them to be, you know, substantially similar. So they're giving very similar results, but you can see that when you consider the cushioning effect, it takes slightly longer for the pipe to get filled up. So that is a SubC pipeline system. Deluge system with a loop. What do I mean by that? Because you're thinking to yourself, oh, well, deluge systems don't have loops. No, not necessarily the case. See, this deluge system, that is actually a ring. So essentially, it's a loop and it's connected at this point. By the way, this is illustration, so please don't say things like we won't have, you know, a cross connection like this. And that is correct. That typically is unusual to have this kind of a connection, but this is only a model. Okay, so it's there to illustrate a point. See, this is nozzle 8, nozzle 7, nozzle 21, and this is pipe 8. So let's see, what would you expect? Let's look at nozzle, compare nozzle 21 and nozzle 8. See, this actually is an example. This shows the beauty of the dry pipe model. See, there are some spikes here. That's on nozzle 21, which is here. I want to show the volume of air in pipe 8 now. Pipe 8. No, pipe 8. Sorry about that. Let's change the colors a bit. Okay. The red line is the volume of air in pipe 8. See, which is here. You can see that pipe 8 actually is full of air. But when the system starts discharging fully, the volume goes down. Why? Because the air gets trapped in this pipe, and when the pressure increases, it gets compressed. See, that's a feature of dry pipe 2. It can model things like this. Let's see that the air cushioning effect is switched on here. And the beauty of this is that the oscillation of the air volume here works all the way back to that nozzle and creates oscillations in the flow rate there. It's quite amazing, isn't it? See? It reaches a peak here, what we would expect, reach a peak and then come down to steady state value. Not so, because the cushioning effect on pipe 8 works its way back to nozzle 21 and creates another spike. Isn't that beautiful to see how the system interacts? We all know, we've always said that when you have fluid flow, the whole system will interact with each other. Now, you see, mathematics shows us how they interact. It's fantastic. So let me now remove nozzle 21 and say show nozzle 8. Now, you would expect, you would see what you would expect, you know, when the air in pipe 8 gets compressed and so on, you know, it creates some oscillations in the nozzle here. And in other words, the air getting compressed here changes the flow rate because it won't simply compress and stay compressed. It will actually change the volume. And as you can see, the volume will oscillate slightly, and the flow rate through the nozzle will also oscillate in response to this. This is why when you open the tap in your kitchen, sometimes you have this kind of gulping kind of effect, and it's because of things like this. It'll be worse if there is some air trapped in the system. Okay, and mathematics is so beautiful that it can predict all of that. So that is this closed. Now the question is, you're curious to know what will happen if I did not consider the cushioning effect. You know, essentially, PIPENET will do the best it can. It will simply say that this pipe here is going to be full of air or whatever is the case may be, but you won't see this cushioning effect. See, the volume of air just goes to 0 from the initial volume. Okay, because as soon as water gets there, and because we're not considering cushioning effect, PIPENET will assume that it's completely full of water. It has gone up in more or less an instant. So if we have dry pipe 1, before the launch of dry pipe 2 model, we only had dry pipe 1, but this is something we had to model, and this is the model that Dr. Chen developed. See, do you remember I said to you, we can put a buffer pipe, which is an extension of the pipe. It's a bit like that. There are, we're putting extensions on all the pipes, including those ones, to these up here to reduce the pressure surge. And this may take longer to run. If it takes too long, no, it's not bad. Nozzle 8. See, we have a little bit of that oscillation effect. Nozzle 21. Which also has the scales are the same. Okay. So you can see that there are some oscillations because, but they're slightly different because of the way we're modeling that. So if you want to use dry pipe 1, you have to put some accumulators at the end of the system in order to model the cushioning effect of pipe 8, which was here. Okay. Now let's look at the next example here. Before I go to that, I'll show pictorially what we're looking at. That's the system we're looking at. I'll open that. Okay, let's zoom in a bit more and have a look at it. See, we've got this kind of arrangement here. Why have we got this arrangement? Because this actually models a fire pump of this type. This concept of fire pumps was actually is attributed to Frank Mohn Pumps. That's a Norwegian company, and it's gotten a surge tank or surge suppression device, which is an integral part of the fire pump system. So when the pump starts, that's a sea level. When the pump starts, that will rise, and you know that's the minimum flow, but that's the flow into the ring main, and you know there will be some shock waves potentially, and the surge tank will actually suppress that shock wave. You know, those of you who've done surge analysis with offshore fire water systems, you will know that there are two main problems you should consider. One is pump startup, because you could create pressure surges here during pump startup, and the other is the deluge system startup, during which time you could get pressure surges in the fire water ring main. And you know, typically here, in order to suppress a pressure surge, Frank Moore introduced an integrated surge tank. And a classic solution for solving the pressure surge problems in the fire water ring main is to install vacuum breakers. That's what we've got here. So we've got the minimum flow line here. It's a short bit of pipe, connection to the fire water ring main here, and then there's a surge tank. Let's look at the corresponding PIPENET model. See that there's an air release valve. You can see that there is an air release valve here as well, because the last thing we want is for air to go into the fire water ring main. And so there's provision for air to escape. So that's this air valve here. You can see that it can allow air to come in and air to go out. Because why? Because when the pump stops, you want air to come back into the system. Otherwise, you will have a cavity which could stay there. And when you restart the pump, the cavity can collapse, creating a pressure surge. So you allow air to come into the system, and also you have provision for the air to go out. And the surge tank itself is modeled as dry pipe 2. See, consider air cushioning effect. And then there is a dry pipe here and there, and that's the minimum flow valve. See, ironically, this bit of dry pipe here, which is 10 meters long, is very long. And that actually creates the worst pressure surge in this case, because that happens before the surge tank becomes effective. So you've got to be careful about how you design. Maybe you should use a shorter pipe here, because that creates, is what happens is water actually hammers into this dead end. There's an air column here that's highly compressed, and then it starts oscillating, and hence this is a source of pressure surge. It was quite an unexpected discovery for me. So anyway, that is how you model the Frank, or the company is now called Frammo, I believe, not Frank Moore anymore. And this is how you model that pump. And this, those who've done surge analysis, you already know what this is. This is a way of representing the jockey pump. You give a pressure spec of 7 bar, and this valve closes very quickly to begin 0 to 0.5, and that initializes the pressure here. And you must put this valve and close it. Don't just put keep the valve open, because then when the fire pump starts, it'll push the water back here. Alternatively, of course, you could input the jockey pump explicitly here with a check valve, and that is an alternative you can consider. And if you look at the deluge system, there is a clack valve. Clack valve is the traditional deluge valve, which only has two states, fully open or fully closed. It doesn't control the downstream pressure. And that's what we're considering here. So let's run it. By the way, if you have a valid license for PIPENET, we can send you some of these data files. Of course, we cannot send you the data files if you do not have a license, because you cannot run it. So please contact Victoria if you would like to have the data files for the examples that I'm showing here, and we'll send them to you if you're a licensed user. We would appreciate it if you could, send us your key number. This is a more complex deluge system than the one we looked at earlier. So that's why it's taking slightly longer, because there are a lot of things going on. There could be oscillations in the pressure here. And of course, as I said, that pipe here, much to my surprise, I discovered that that's a source of a problem. Okay. Nozzle priming time. Let me change the font size. You're going to change it as the first one. So, see, that's 31.7. Of course, we could always say, go to this. $31.66. Don't know where it is. And that'll take me straight to the last nozzle. You say, although it seems to be slightly at a lower level, it's got this pipe in addition to everything else here. So it's clear that that is likely to be the last nozzle to prime. See the maximum pressure. You can see that here in this pipe, it is 47.2. This is what I was talking about earlier on. The surge tank here, let me reduce the font size a little bit. See, that's a pipe. It's got a high pressure. The rest of the system is fine. Wherever you look, there's some high pressures here, so you'd have to do something about that. If you put the buffer pipe I was talking about here, that will almost certainly bring down the pressures there. Whereas the system has got this vacuum breaker, the air inlet, which is typically larger when you're using the vacuum breaker to reduce pressure surge, and the air outlet is 20 millimeters. So the air comes in more easily than it can go out. That's important. Okay, so this is how you would model vacuum pumps. Let's see what happens if you remove this vacuum breaker. I'll ask for the results. of these pipes as well now. So if you look at the elevations, see the high points here are 8 meters. Where here, this is 18 meters around here. So the helideck, it's normally the case. The helideck is at 18, whereas this deluge system goes up to 8 meters. And the datum is the pump. Okay, so I'm going to remove, and usually you place a vacuum breaker at the highest point here. So let's see. I'll take this opportunity to have my cold coffee now. So you can see that the 5-watt ring main is all flooded, whereas the deluge system is dry, so it's a conventional kind of system. And, you know, and the actual elevation change is not, it's a little bit exaggerated because that's the elevation change is around 5 meters or so. So it's not a huge elevation change. So you must avoid big elevation changes in a dry deluge system because that will extend the discharge time significantly. So that is good engineering practice to try and avoid big changes in the elevation in the dry part of your deluge system. See? All I did was to remove the vacuum breaker. And look at the huge difference it's made to the results. We look at pipe 8 and pipe 11 to see what's going on there. Pipe 8, what's that here? Look at pipe 11. See, that's a cavity volume. So you can see that the cavity volume is oscillating a lot. The pressure in pipe, you can see that it didn't show that 131 or whatever it was, because 113 or whatever it was, because, you know, that was this fact. The graphical output time step 0.2 was the calculation time step is probably smaller than that, okay? And by the way, this is a very, very important point, and I must point this out. And always keep this in mind, because there is this thing called smart output, and that will catch the peaks and the minimum values, okay? So that's what we're finding here, that if I remove the vacuum breakers, the pressure surges increase enormously. And, you know, keep this in mind. Why? Because that's pipe 8. We look at the results in pipe 8. cavity volume, pressure surge. We're getting is quite a big cavity in the pipe and pressure surge when the cavity collapses. Okay, so this is one way of modeling fire pump with an integrated surge tank, and typically that's Frank Moore pumps. Offshore fire water systems with elastomeric valves see, we've got an elastomeric valve. This is the way we suggest you model an elastomeric valve. And we've assumed that the philosophy of the way the elastomeric valve works is here. The fire is detected at 1 second into the simulation. That's our assumption. So the system is in its quiescent state for 1 second. Quiescent means nothing happens. It's in a steady state, no fire is detected, and the system, it is a standstill. That's the first premise. The fire water pressure in the ring main should be at least 2 bar. By that I mean the pressure in this part of the ring main, upstream of the deluge valve, must be at least 2 bar gauge for the elastomeric valve to work. You know, these assumptions are assumptions we made. You may say it's this elastomeric valve will start to open if the upstream pressure was 1 bar or even 0 bar. It's entirely up to you. It's an assumption I'm making that this elastomeric sleeve needs 2 bars upstream to open, otherwise it will remain closed. And if these two conditions are satisfied, in other words, it's 1 second into the simulation and the upstream pressure is at least 2 bar gauge, then the deluge valve will regulate or control the pressure downstream. And these are the assumptions we've made in creating this model. You may have different assumptions, in which case you would have to change the loop here, the control loop, a little bit. Now let me first explain, because more and more offshore systems are using elastomeric valves, so I will explain how this is actually built. First thing, we've given a constant value. That's an information node. That's called a signal selector, which is here's some of that one there. See, that can be used for a number of in a number of ways, but it has 2 signal inputs and 1 signal output. And what is this? See, there are different options you can have. This is switch time. In other words, up to 1 second, it will use that input. After 1 second, it will use that input. Okay. So the output of this will be that value up to 1 second. So it will have 0 here. And after 1 second, it switches to this. And we have a pressure switch here. See, which turn on about 2 bar gauge, and that's a pressure sensor. So when the pressure here reaches 2 bar, that'll switch on, which means that that will become 1. When it's off, that'll be 0. When it's on, that will have a value of 1. Now look at the output of the signal selector. It will definitely remain at 0 for the first 1 second because it's going to switch. Until 1 second, it'll use this. After 1 second, it'll use that. And that will be 1 if that was 2 bar or more, and it'll be 0 if it's less than 2 bar. That's the value here. So it can be either 0 or 1. What does this signal selector do? It chooses the lesser of the 2 values. So when this is 0, that value would be 0 because it'll choose the smaller of these 2. So if the time is more than 1 second and the pressure here is 2 bar or more, the value would be 1 here. And the output of a PID controller can only lie between 0 and 1. Because if it's 1, it means this valve is fully open. 0 means it's fully closed. So it can only have 0 and 1. So it will choose the value, the output of this PID controller here. So that is the way this is designed. So let's run this very quickly. It's actually quite a complex, you can see, it's quite a complex model. I mean, first of all, you've got this overboard dump valve that closes, and then we've got a dry deluge system which needs time to prime. It's a very complex calculation. The network looks simple, but the calculation, you can imagine how difficult it is for PIPENET to see how the flow goes along the line and all these pipelines, and then how the nozzles discharge one by one, and all those things. On top of all that, we've got this control systems here. Control systems are actually quite difficult, more difficult to model because of the feedback effect, that it is actually doing a lot of things because it's checking all the time that the pressure here is more than 2 bar. And, then it's, of course, it's got to model the PID controller and then, select the signal between these 2 and so on. So it's got a really hard work to do. We can look at the position of that valve. That's valve 7. Valve 7, where is it? Here we are. So look at this. This is fabulous because you see the firewall ring name is initially at 7 bar because the choky pump maintains 7 bar. So after 1 second, the signal switches from here to there, and it sees 7 bar here. So that'll become 1. See, so this control system then takes effect. And so we find, see that valve opens momentarily. And of course, when the deluge valve opens, the pressure in the ring main collapses because the fire pump hasn't started delivering water yet. So it opens momentarily, it closes. And of course, the system gets primed, the fire water. If you look at the caisson, number one, let's look at that. Caisson number one. See, unfortunately, this little panel you probably can't see, which comes from the GoToWebinar which we're using. See, that's a height. So this is how the caisson gets filled up. Very shortly afterwards, the valve starts to close, is open, because the pressure here goes above the required pressure minimum of 2 bar once the fire pump actually repressurizes the fire water system, ring main. But of course, it takes time for the PID controller to respond. And so it takes time for that valve to open. And of course, it overshoots because all control systems overshoot. And so the valve elastomeric sleeve overshoots and then comes back to its final steady state value. So this is how the system is working. Okay, so that's the main point about this model I wanted to show, is how to model the elastomeric valve. You've already seen the dry pipe part of that, so there's not a great deal of merit in going through all that because it'll take time. Next model I want to show is where you have an overboard dump system. You've got a vacuum breaker valve there. But the focus of attention is this, the overboard dump system, okay? So see, there's a low point in the system. Let's say that you designed it not in the best possible way. So there's no drain here. So water collects in that pipe. So that pipe has got water in it. The rest of the system is dry. And we've also, this is a kind of minimum flow line. So it's got some kind of a control system. So the pressure here also has an influence on the position of this valve. And there is a signal selector here. Now this time it chooses the maximum. And here it's not a fixed value. We're saying there is 1 and that is 0. So basically what will mean, if this control system wasn't there, this will close from 15 to 20 seconds. So 15, because that'll give enough time for this pipe to have primed. Okay, that's the philosophy. And because it's a minimum flow line, there is also a control system which can then have an influence on the position of that valve. The main point about this is not that. And, of course, this is useful to know how to create this model. And the main point about this is what happens to this flooded part. We'll speed up a little bit because initialization is a little bit slower in this case. So basically, what do you think will happen? That these pipes will get flooded. When they get flooded, this column of water will get pushed out through the system. It'll be like a slug that flows down the line. And that is what we're trying to model. Okay, and there's of course this control system on the overboard dump line as well, and that is what we're trying to model. And what is of most interest is what happens to the slug of water. Okay, I made a mistake. I didn't put a drain valve here, but I want to see what happens to this. And my expectation is that the water column in this pipe will move down and it'll get expelled, and air, which is in the system, will also get expelled. As you can imagine, we need to use the air cushioning effect in this case. So let's look at some of these. That's pipe 60, 61, and 75. Let's just look at those three pipes, 60, 61, and 75. So initially, let's look at the volume of air. Pump 60, this pipe here, 61, and 75, they're here. Click 61. You can see that as the air actually moves out of, is pushed out of this pipe, the water here also starts getting pushed out. You see, do you understand? That air gets expelled from this pipe, it can't just leave. The only thing it can do is to push the water out of here. So you see? So you can see that the air volume in pipe 61 increases because the air which was in pipe 60 starts coming in, and then it gets full of air. You're talking about this pipe here, and then the water comes in. That's what is happening here. And if we look at pipe 75, I think this is a fantastic model. Because pipe 75, it starts losing because, see, there is water that comes in from here, and that pushes the air out, air volume, and then increases. But don't forget, there is air which was in this pipe that comes all the way. There is another air slug that actually moves through that pipe. And that's, you see that green pipe, the volume of air increases, then goes to 0. So you can see this is a fantastic model. You can actually see how the air pockets moves through the system. It's very, very advanced model, very complicated. Okay, that's the three kind of situations that you may encounter in modeling real systems where we use the cushioning effect and the air pockets. Now go on to some other aspects. We already saw in the previous example how the air pocket moves and how the air column moves. This is a simpler model, but it shows something even more interesting, and we'll show you what happens. This, by the way, as I explained in the beginning, is simply an air inlet valve or vacuum breaker valve, and that's simply an air release valve. And this valve closes and then opens. So let me run that. Okay, now, what is the first thing that's going to happen? When this valve closes, it's closing in 5 seconds. So if you look at the pipe length, see you've got a pipe here, which is 1 kilometer long. And so there is a significant momentum in the liquid in the line. So when this valve closes, 5 seconds is a relatively short time when you've got such long pipes in the system. What would we expect? The first thing that will happen is we can expect some cavitation here. Because the pressure here may not have gone below atmospheric pressure. In other words, vacuum breaker may not allow air to come into the system, and cavitation may start here. So let's have a look at what's happening in that pipe, which is pipe 1. Let's look at the cavity it should be at the inlet. Okay, these are the different grids. A pipe divided is subdivided into grids. And so this is a cavity volume in each of the grids. Wow, look. See, so the first thing that happens is exactly what my intuition tells me, that I'm going to get a cavity here. If you look at the other end of the pipe, see, it's no cavity. Why? Because the momentum is drawing the liquid against a dead end here, not there. So although this is a higher point, the cavitation actually starts here. But soon, see the pressure here, because the valve is closed, because of the static head, the pressure here will drop below atmospheric pressure. because that is equivalent to minus 2 bar. So let's look to see the volume of air in the pipe 1. See, that's a volume of air. And that actually reaches more or less the same volume as the cavity. See, it's fantastic, isn't it? That you have a certain cavity volume that's created. When air comes in, the volume of air in that pipe is equal to the cavity volume, because that gets filled to that volume of air in that pipe. Okay, so that's what is happening here, which is exactly what I would expect. We can also look at what's happening here, in particular pipes 2 and 3. We can look at this. I believe this is vacuum break 1, air valve 1, that's air valve 2. We can quickly look at those. Air valve 1, the mass flow rate, let's look at that. Why is it like this? Because there's a vacuum that forms, air comes in. Don't forget, this is negative. Any flow into the system will be negative. So air flows into the system, and then the flow rate of air stops. It's not constantly, because when the valve closes, air will come in, and then air flow rate will stop. It's a little bit deceptive because the scales are different, and because the diameter of that valve is 50, and this valve is 15, is quite a big difference, because you're talking about the area of cross section. See, the flow rate is bigger in the air release valve, but its the duration is much shorter. So air comes in here. It takes a little while for the air pockets to move to the air release valve and then goes out. So essentially, air comes in here, moves down to the pipe, and then goes out through that. We can also look at what happens in pipes 2 and 3. So let's move. Let me just delete that. Pipes 2 and 3. See, that's pipe 2. Air comes in and moves down that pipe, so the volume of air goes here, and ultimately there's a pocket of air which moves down that pipe. You can see that, and it then goes to pipe 3. Because pipe 3, by the way, it'll get a little bit of air when pipe 2 gets full. I mean, here pipe 2 is full of air, so don't forget. This is where pipe 2 starts getting air, and when pipe 2 gets full of air, it's the top, pipe 3 starts getting an air column. This remains full of air until the valve fully opens. Do you remember the valve opens at 50 seconds and finishes opening at 60 seconds? And then the air pocket in pipe 2 disappears, and pipe 3 will ultimately see the air pocket volume in pipe 3 also goes down, and then it gets expelled. See, when this is the line of the airflow rate through the air release valve, mass flow rate, and then when it flows out, the volume of air in pipe 3 goes to 0. Isn't it fantastic? So you can see this is how you can follow the movement of the air pocket. I'll just show one more simulation here. This is a pretty quick one, and then we can finish. This is really a model that compares the air valve to a vacuum breaker valve. What is the difference? See, these simulations are actually very complex, because you can see how difficult it is to model how the air pocket moves with the system. Comes in here, moves down this line, and goes out through there. That is reality, but you can imagine how difficult it is to model that. This is pipe 10, pipe 1. Pipe 1 is, by the way, this valve is closed. You know, we've got this valve and it's closed only to make sure we have one connected network. That's what we need. So let's look at pipe 1. Cavity volume is exactly the same as what we saw before. Let's compare that to pipe 10, which is here. This is dry pipe 1, and that's dry pipe 2 because of the connection of the air valve. It's the same, but there are some oscillations. But let's look at the volume of air. See, the volume of air is 0 because we haven't got an air valve, we got a vacuum breaker valve. The vacuum breaker valve does not model how the air goes into the system. If you compare that to pipe 1, see, pipe 1, you get an air pocket that comes into that pipe when the cavity in that pipe collapses. So see, this illustrates the difference between the two models. Anyway, I've said everything I wanted to say, and shut up now. I'll just say thank you for being here. You know, time is the most precious thing we have apart from our families. And thank you for giving up your time to be here. And I hope it was enjoyable and it was useful for you to see these capabilities and we hope that this would improve the use of PIPENET by your company, and it's another additional skill that you've learned. Thank you very much. Wonderful to see you. We love to see our customers. Thank you very much for being here. Thank you. I'll say bye-bye. Victoria?
Dr. Sebastian, thank you very much for delivering this session. And thank you to all our guests for staying here. And we hope it was really useful and enjoyable to you. Chelvi, Legend, are there any questions which are still unanswered, or have you managed to answer all the questions in the chat?
Yes, Victoria, you can proceed.
Okay, thank you very much, Chelvi. So if you have any questions left that you still think of, please feel free to email your questions to us. You have our email addresses, it's pipenet@sunrises.com, or write to me, Victoria@sunrises.com. You have our email addresses. As I said before, we will be happy to share the video recording of this session with you either later today or tomorrow. And if you would like to receive a certificate of attendance, please drop me a line and we will be happy to send you a certificate. If you are a customer and you would like to receive some of these files, again, please write to us and we will be happy to share the files. Thank you for your attendance. Thank you for your attention. And we look forward to seeing you at our future webinars. We are planning to host more webinars this year, so please follow our announcements, and we look forward to seeing you again online. Thank you. Have a good day, have a good evening, and bye-bye.
Thank you all. Thank you. Bye-bye.